Hello students, in this video we'll discuss additive and multiplicative properties of convergent sequences. So let's suppose that AN converges to A, BN converges to B. You can see how this notation saves us a lot of writing. So AN converge to A and BN converge not to A but to B. Doesn't have to be A, it can be anything. So let's put a B over here. Then we have two things. Then number one, the sequence AN plus BN, when I add the sequences, add the terms of the sequences, will converge to A plus B, as we expect. And two, AN times BN will converge to A times B, the two algebraic properties. We can even throw a third property in here, which is fairly obvious, that if I have C times a constant times AN, that this will converge to C times A. So let's prove all three of these things. So here's the proof. And during this proof, we'll introduce a common technique that's seen in these analysis proofs, where you sort of have the right idea of which epsilon you need to choose to make things equal epsilon at the very end. So let's do the following. Let's choose, let epsilon be greater than 0. This will be the proof of number 1. Let epsilon be greater than 0, and pick N1 and N2 in N, such that two things happen, such that AN minus A less than epsilon over 2. You might say, where's the epsilon? And then BN minus B is less than epsilon over 2. And this is true if N is bigger than or equal to N1. And this is true if N is bigger than or equal to N2. Okay. Now the epsilon over 2, if you're made less than an arbitrarily small number epsilon over 2 is still arbitrarily small. So if I can choose it for epsilon, I can choose it for epsilon over 2, I can choose it for epsilon over 3, I can choose it for epsilon squared. In some sense, it doesn't matter what function of epsilon you choose over here, as long as that function is what? The function needs to be on the same slope, in the same basically direction as epsilon, as the same operation as you're decreasing to 0. All right, good. So now, if N capital is equal to the max, our common trick of N1 and N2, and N is bigger than or equal to N capital, then AN plus BN minus A plus B is less than or equal to, I'm going to group the A with the AN and the B with the BN. And I'll use the triangle inequality to say this is less than or equal to AN minus A plus BN minus B. Now this is less than epsilon over 2, and this is less than epsilon over 2, because we're bigger than N, and N is bigger than the maximum of those two things. So this is cumulatively less than epsilon, and that is our proof of the first proposition. So we chose the maximum. Now, we would like to show that AN minus, so let's sort of see how this epsilon over 2 was put into the proof by looking at the short work. So that's the proof of 1. Let's sort of sketch 2 to see how we'd write the formal proof. So here's the sketch of 2. And the sketch, of course, is what allows us to write down the formal proof. So the sketch of number 2b. Well, what we'd like to show that AN times BN minus AB is less than epsilon. That's our goal. That's what we want to do, right? Now I would like to see an AN minus A and a BN minus B. So what we can do is we can sort of manipulate this to be AN, BN, and I'm going to subtract off an A times BN, and then I'm going to add in an A times BN. That will be fine. And then what I can do now from those first two terms, I can factor out a BN. So this is the absolute value of BN times AN minus A. I see my AN minus A, that's good. And then I have a what? I'll factor an A out from the second terms over here. And then what? And then we'll have a factor of BN minus B, right? The triangle inequality will say this is less than or equal to the absolute value of BN times AN minus A. Plus what? Plus absolute value A, and then BN minus B. So now we can sort of see if I want all this to be less than epsilon, what we can do is the following. We can now, that's our sketch, and so let's see how the sketch can be turned into a genuine proof. The sketch can be turned into a genuine proof as follows. Let's let epsilon be greater than 0 be given. And let's pick n1 such that Bn is less than or equal to a constant c if n is bigger than or equal to n1. And here I'm using the fact that convergent sequences like Bn are bounded. So convergent sequences are bounded, so I can ensure there's an n1 such that this happens. I can pick n2 such that, so pick n2 such that what? Such that, well, now I have this Bn times an minus a. I'd like to choose n2 such that an minus a is less than epsilon over 2 times the c that we found. Then this whole term over here, the Bn is no larger than c. The an minus a will be no larger than epsilon over 2 times c, so I'll have a c times that c in the denominator. It'll cancel out, and this whole expression over here will give me an epsilon over 2. And finally, let's pick n3 such that what? Such that Bn minus b is less than epsilon over 2 times the absolute value of a. And now, those are the components of our proof. So now we can put all this together and say, what can we do? I can write down the same exact expression. So then an Bn minus ab, if what? If n capital is equal to the max of n1, n2, and n3, and little n is bigger than that, this n capital, then this is less than or equal to what? Bn times an minus a plus absolute value a plus times, of course, that's a times the quantity Bn minus b in absolute value. Good? And so now what? And so now we can use all of our conditions one by one. So let's use our conditions one by one. So of course that's just absolute value a. Make it a little bit cleaner. And so now of course this is less than or equal to c because we're bigger than the threshold n1 where all the Bn are less than c times epsilon over 2 times c plus modulus a, or absolute value a, times what? Epsilon over 2 absolute value a. Now the c and the c will cancel, the a and the a will cancel. I have epsilon over 2 plus epsilon over 2. That'll be less than 1. Of course, this is going to be less than, strictly less than by our assumptions. It's a force of habit that I'm always writing less than or equal to, because in most analysis, you care about less than or equal to, that's just strictly less than. And then we have over here just equals epsilon. So an Bn minus ab is less than epsilon provided that n is bigger than the maximum of n1, n2, and n3, and that's our proof. Now, in particular, I can get number 3 for free because I can choose Bn just to be the constant sequence b. So if Bn is identically equal to b, that's a constant sequence, and that clearly converges to b, then, or in this case c, then a constant, we can turn that into a b, then clearly any constant b times an will converge to ab by the previous result. Thank you very much.